You good? Okay, good morning. So my task this morning is to present some of the literature, the emerging literature on 1.5 mitigation scenarios. And as we know, in the fifth assessment report, there was not much information available on 1.5 degree pathways. So if you think about 1.5 degrees and 2 degree pathways, a lot of questions that emerge and a lot of things that are investigated are common to both. And then there's the question of how do they differ? And I will try to address both of these questions in the presentation. If you think of deep decarbonization, really going to very ambitious climate targets, we of course look at strategies that affect all regions and all sectors. So these are scenarios that imply emissions reductions in all regions and all sectors over the 21st century. And a usual tool for these types of investigations are models that cover all sectors and all regions over the 21st century. So let me start off with the Paris Agreement. The Paris Agreement, of course, has taken note of AR5 and the IPCC work. And if you look into the targets that are set out, you not only find, as we all know, the temperature targets, but you also find some specifications on the emissions pathway that they foresee to reach those targets. One is, of course, to peak global emissions as quickly as possible, but then there's the second provision to achieve a balance between emission sources and sinks in the second half of the century. Definitely leaves open the possibility to use carbon dioxide removal technologies in order to reach these targets. So this has been clearly informed by IPCC work. So in order to look at the challenge, there's this very powerful graphic that was produced in addition to the climate spiral by colleagues like Malte Meinshausen and the Prima project at PIC. And you can see how we fill up the atmosphere with carbon. And it's really the accumulated greenhouse gases emissions in the atmosphere that matters for temperature and for global warming. And you will see the 1.5 degree budget here, put up the 2 degree budget, and what this graphic clearly shows is we are on a crash course right now. So emissions increase and have increased until now. We have to see whether we are going to see a peak fairly soon. But the big question is, how can we stop this trend? The first thing is we need to go to zero emissions eventually in order to stay within the budget and to stabilize temperature. Before we do that, though, we first need to reverse the trend of increasing emissions. Peak and go down, and then do a rapid emissions reduction in order to stay within this limit. And the question is here for 1.5 degrees, can this happen fast enough in order to reach 1.5 degrees? So before I go into 1.5 degree pathways, let me talk a bit about the general structure of these emission pathways. And you don't need actually a model in order to come up with these shapes. If you look at these shapes, there are model results behind it. This is a study we did in 2013 in the run-up to the Paris negotiations. We called it Durban platform scenarios at this time. And here you see a median 2 degree scenario. So it's a 50% likelihood of reaching 2 degrees. But the structure of these pathways are the same, whether you have a 2 degree, likely 2 degree pathway or a 1.5 degree pathway. You have an early peak as early as possible. At some point you reach carbon neutrality in the second half of the century, going through the zero line here. And in between you have steep emissions reductions. And then, if you look in the underlying dynamics of these pathways, at the time of the peak, the story is really about redirecting investments. You want to reverse the trends, so you need to really redirect investments from fossils to renewable energy so that you really can change the trend. When it comes into the phase of steep emissions reduction, the power sector goes first in these scenarios, so it's decarbonizing very rapidly. And the other important element, and it cannot be emphasized enough, even though we all know, is the coal phase-out. So if the world decides to increase renewable energy significantly, but at the same time decides to leave coal alone, then you won't get the emissions reductions that you want to see by 2050. And actually, if you see different levels of emissions reduction in 2050 between models, the first thing you do, you look into the coal use in these scenarios, and you can see where the difference is coming from. So phasing out coal is really important. Then we come to this time of carbon neutrality. And this is a time where we really need to think about how a carbon neutral economy could look like. And here the big questions will be, how do we get rid of these very hard to eliminate emissions? These are particular emissions in freight transport, aviation and shipping, heavy industry, and agricultural emissions, as we also heard yesterday. And so these, as we might call it, decarbonization bottlenecks are really important. I think a lot of research should go there in order to look for ways to do this. Currently, many models use biofuels to decarbonize here. And that's independently whether the biofuel use is then coupled to CCS. So even if you have a scenario without BECCS, it might have substantial bioenergy use with all the sustainability implications of it. And then in the end of the century, you have in these scenarios, and in most of these scenarios, net CO2 removal by using carbon dioxide removal technologies. BECCS is the one that is most prominently used in the models, but there's also afforestation in some of these scenarios. And they have two uses. And the first one is the more important one in the scenarios. That is to compensate residual emissions that you have at the time. So if you don't manage to get rid of these very hard to decarbonize emissions in these sectors, then you can compensate with carbon dioxide removal technologies. We also, at this time, in this study, looked at scenarios where you wouldn't peak immediately in 2020, but delay, we called it delay, until 2030, this trend break. We called it Durban failure scenarios at this time, not anticipating that this is kind of an INDC development that we see right now. So it's not appropriate to talk about failure because Paris was a big success. But it also points to the fact that we have the Paris Agreement, that it enters into force, is very important, but it's just the beginning because we really need to get this peak, to see this peak. Otherwise, we're looking at much more complicated pathways where the peak is higher and later, where the carbon neutrality, because you have a fixed budget, needs to come at an earlier point in time, meaning that you're really squeezing this transition period from the peak to the carbon neutrality needs to be much steeper, and in the end you might also have to do more carbon dioxide removal in order to compensate these excess emissions. You can already see, the longer you wait, the more this transition period becomes infeasible. So we can say, and we might see research coming out, that really if you stay on this INDC trajectory until 2030 and think, oh, we will strengthen thereafter, that your targets are no longer in reach. But at the time we did this study, many people were very skeptical about getting a global agreement, and we were positively surprised, so we might be positively surprised again that indeed there will be more done until 2030, not after 2030, under the umbrella of the INDCs. That's critical, and for me that's the biggest question right now. How can this be achieved? So now I'm going in the direction of 1.5 degrees. And I'm showing you this iconic figure from the synthesis report of AR5, where you can see this linear relationship between cumulative anthropogenic CO2 emissions, the CO2 budget, and temperature change. I think that was a very important finding of Working Group 1 to establish that relationship. And superimposed on this, you see these various scenario types that have been run in Working Group 3. And you can see in Working Group 3 of IPCC, you can see it was going down to the 430 to 480 ppm CO2 equivalent range, which is a likely 2-degree scenario. So now we want to look into 1.5 degrees, which sits down here. And there's a number of studies now that are currently working on these scenarios, and there has already been one published that looked at these scenarios from two models that emerge as side products of sensitivity analysis. So those scenarios are not from studies targeted to 1.5 degrees. These are just side products of sensitivity analysis, and what we need now is to get really dedicated studies on 1.5 degrees. This shows you the budgets of those scenarios. So you see 3 colors, 3 types of scenarios. The blue ones are the ones of greatest interest today. That's the 1.5 degree scenarios. And on the x-axis, you do see the budget from 2010 to 2050, so just the next 40 years. The budget over the entire century is on the y-axis. So if you're on the line here, on the diagonal, it means that you wouldn't emit anything in the second part of the century net. If you are below the line, it means that you even compensate some of your excess emissions until 2050 with carbon dioxide removal in the second part. And you can see this sensitivity study has only scenarios that really have a very strong carbon dioxide removal in the second part of the century. But already the 2 degree included that. So one question will be, what are lower limits for CDI in order to still reach 1.5 degrees? And that's a question we need to explore in the coming year. This is a picture of the pathways that emerge from this study. And you can see this general structure, which I've introduced here. Peak is very early. You see some scenarios that already are infeasible because they peaked in 2015 and then drop rapidly, but others that increase until 2020. And the one noticeable difference is 1.5 degrees means you need to get to emissions neutrality earlier and also to carbon neutrality. And here's another complication. Here I'm not showing CO2 only, I'm showing CO2 equivalent. So that means even if you have negative CO2 emissions, you might still have net zero greenhouse gas emissions if you use global warming potentials to aggregate these emissions. So it's 10 to 20 years earlier. It actually means that you need to decarbonize by 2050, fully get rid of carbon in these scenarios. Then looking on a broader set of CO2 reduction metrics, you have, that's a fairly complicated figure, on the left-hand side, and very important indicator, cumulative carbon dioxide removal, 2010 to 2100. This always there's a lot of discussion about that. It's an important indicator. Then the decarbonization rate in 2010 to 2050. So how fast do you need to go down? And then in various sectors, electricity, industry, transport, and buildings. And this is now a comparison between 2 degrees and 1.5 degrees. So here, the circle gives you the 2 degree effort, normalized, and then the question is how much does it increase in terms of percentage if you go to 1.5? So you get this range between, there's an uncertainty range because these are a number of scenarios, and you can see definitely that you get more reductions from the building sector as well as from the transport sector. In these scenarios, you have an increase in decarbonization pace, and that doesn't look very significant, but it is significant because it's percentage per year. And what you also see is carbon dioxide removal is not increased as much between 2 degrees and 1.5 degrees in this particular set of scenarios because the models already used carbon dioxide removal close to the limit of the potential they have seen in 2 degree scenarios. So this is the type of results that we need to check now and robustify and see whether that's really properties of 1.5 degree pathways. That's what I just said. Now let's come to some of these studies that are right now ongoing in order to get a better understanding of the properties of these 1.5 degree pathways. One is the advanced study, that's a Horizon 2020 project that is finishing up right now and has taken 1.5 degrees on board of their final scenario study, which is mainly targeted to look into INDCs and the implication of the INDCs for the energy transformation in the long run. But it also looks, as I said, into 1.5 and 2 degrees pathways. Just one result, and these are preliminary results, so should not be circulated or published already, is to compare how much fossil CO2 we really have in these scenarios, and that basically implies how much we need to compensate with carbon dioxide removal in order to stay within the budget. And here you can see 3 scenarios. The one is the INDC. I think I have a pointer. Yes. An extrapolation giving you a lot of carbon dioxide emissions. You have a 2 degree, a likely 2 degree, and a 1.5 degree. And you can see you get some extra reductions by mitigation options. But there's some limit here. You're running against a lower level. And the question is, of course, are there some 5 minutes? Oh, that should work. Are there some technologies that could get us deeper here? On the other hand, in order to stay within the budget, you see an increase in these carbon dioxide removal technologies. So this is mainly BECCS in these scenarios and afforestation, going down to about 700, on average, 700 gigatons CO2 from 500. So there's some increase, but it's not a dramatic increase compared to 2 degrees. Another important point I want to make on this set of scenarios is the important role of energy demand reduction. So what one could really see in this set of scenarios, those scenarios that have lower energy demand assumed in the baseline have a much easier job in order to get down to 1.5 degrees. And I think that's another important factor to exploit more clearly and to work out that energy efficiency improvements are a crucial enabling factor for 1.5 degrees. And that also probably not only probably, but certainly will hold for the agricultural emissions, meaning that also less food waste, dietary changes will play a very important role in order to go down to 1.5 degrees. Now, in exploring this dimension of different demand assumptions and different socioeconomic developments in terms of what type of population we look at in 2050 and 2100, what type of economic growth will we have for the century, there's another study now going on to develop 1.5 degree scenarios based on this framework of shared socioeconomic pathways, which are very different in these key characteristics. And this particular work will then also provide a 1.5 degree emission scenario for the next round of climate model runs for AR6. So that won't come in time for the climate model runs, won't come in time for the special report, but for AR6 it will come in time, hopefully. So now I have to finish up, I guess. Coming to this important and very difficult issue of socioeconomic implication of 1.5 degree pathways, there's a narrow lens to look at the direct mitigation costs, just the impact of higher prices, energy prices on the economy. And you can see that many models see this strongly increasing curve of mitigation costs, just showing you 2 degrees, median, and 1.5 degrees. Of course, you can look at more indicators, and you have to look at more indicators. That is what the Rögeli et al. Study also did. I'm going to skip this because I need to finish up here. I do want to give one note of caution when we talk about these cost concepts. They are hard to communicate, hard to understand, and often do not relate to the real world, because what you have in these models are idealized implementations with only the climate externality being a market externality, and then you can evaluate those in a conceptually clear way, which is very valuable, by the way. But it's not those costs that you would see if you implement it in your country. This will depend on your environment. Do you have a savings glut as we have right now? Do we have unemployment and these kind of things? And how is the policy implemented? It can mean that you actually have a double dividend and you have some even benefits, but it can also mean that the costs are much higher. And there's a lot of empirical work to do on this. And then there's this other dimension here that we're not thinking only about climate, but we also have other policy objectives that affect our welfare. So I think I have to finish here. Thank you.